I will talk about speech intelligibility. I will talk about measuring and and also the factors, just shortly the model, and masking and masking release. And so this AI STI predicting masking release. Okay, first the models, general model short, and you have the speech material, then you have a talker, speaker, and then you have a channel, the acoustic surroundings, and then you have the listener, and then you have the response. Yes, I'm mostly concerned about the channel now. So you can have this SNR in speech to noise ratio in dB. Is a difference between the signal or tone dB minus the power of noise in dB. So the intensities should be correct. Yeah, but we are working in decibels. Yeah. So we are comparing between groups. How can we do that? We have SNR ratio in dB, and we have this percent correctness, for instance, of words. And this is the same as 100, of course, because it's per percent, times the right words divided by the total words. Yes. And we have this psychometric functions. I showed two way to compare. How can we do it? There are two ways. You can see, say, if you have a specific SNR, what is the difference in speech intelligibility for measured in this percent for the two groups? Or you can say you want a specific speech intelligibility percent. What is different in SNR? Okay, yes. And SNR is important. It's from I think Tom Poulsen from Fundamentals of Acoustics. Some dental young people, dental untrained young people, normal listeners, of course. There's some result from this, just to that's good to be clever of. You can say if you have minus 15 dBs, minus 5 dBs, minus 15 dBs in speech to noise ratio maybe gives 10% speech intelligibility, and then but if you're increasing to minus 5, it gives maybe 70%. So just a change for the background noise and reducing background noise by 10 dBs, it could increase the speech intelligibility very much. SNR is not enough. You can have this masking, and I'm not taking this course. What's called speech signal processing. But if you have some two kinds of noise, you have the spectral density. Spectral energy distribution is the same for the two, and RMS power and all this and that. It was not great. I could do it again. Shit happens. So, or the opposite. There are dips here, and dips brings masking release. It's easier to, if there's some dips in the, we have time here in the amplitude, so it's easier to understand. The evaporation fills the gaps, the dips. Or evaporation decrease speech intelligibility. So you can say you have a curve here and time, reverberation time, and speech intelligibility. If we do like this. So masking also have a thing to say. Yes. Then I will talk about this AI, STI. Yeah, of course, hearing loss. So many times listeners also have an impact, hearing losses and all this. For me, it could be a very interesting thing, not for young people. Articulation index is an articulation between what 0 and 1 is an old one, but it's just how to predict speech intelligibility. You can say it's an engineering way or something about numbers, but it's sum of independent frequency bands with a importance index here and audibility index, and each band we have that the speech now AI, the speech audibility here is a speech level minus the maximum of the hearing threshold and the noise. Yes, and yes, you can say those speech intelligibility. You have some boom boom frequencies here, and yeah, and you have some importance here. Maybe it's 0.8 or something. So very low frequencies has small importance, and big frequencies has also lower importance. Here, even 8,000, maybe 200. Yeah, in the middle. Okay. So I can also say that yes, that's it. And then we get a number, and then this AI index is transversed to speech intelligibility. For instance, if you have numbers or very, akakadabra is easy to understand. You just need a small AI, and but if it is a very complicated lecture, so you need a bigger AI to get the same speech intelligibility. Yes. Also, yeah, how you speak. Yeah. So if your visual cues are also important, then you have this. Yeah, again, envelope versus time fine structure. Fine structure for low frequencies and envelope for high frequencies. Yeah. So we have this STI. No, STI. We have uh, uh, we have this. Let's say MD1, a modulate amplitude modulation MD1, and we have a speaker and we have a receiver. So the signal is smaller. Here we have A1 times 1 plus cosinus to 2 pi f, the modulation frequency, and here we have M less than 1. It turns out that the SNR in total can be a sum of all the frequency, octave frequencies from KD1 to 7, I think, times it's a weighting factor and times the average over TI transfer index KIF. Yeah. Yes, and this gives the SNR, and you have to translate it to speech intelligibility. Thank you very much. 14 modulation bands and frequencies and 7 octave bands.